Okay, let's get started. So, hello everyone. My name is Andy, and today I'm introduce a topic on Method 24, section 3.5. Calculus 2, 1. So this will be the first kind of topic right after the perspective. Will be section 3.5, implicit differentiation. So what is implicit differentiation? So in this cases, we will find if a function involves more than one variable, like a two variable x and y, if a function involves two variables, for example, x and y, we all need to implicit them and write them into dy dx form. Turn it into dy dx into dy dx. Form is y x into function. So that is like we just, and this is not saying it's a product rule, but it's a, and you will know they're also they're in product form. So this will be kind of the same as partial derivative in 6, but it's not the same way. So how to simply differentiate a function so for example, so when differentiating x variable term, y is not moved, y remain unchanged. And when differentiating x variables, the y variables and an x term, no change. variable terms, x no change, but write out dy dx because dy dx is a term of a derivative. Make sure to write out dy dx. So let's try an example to see how implicit differentiation works is example 1, implicitly apologize for the asshole because like there's something just worn off and I don't know what hell's happening. So because this is just myself at this auditorium. I apologize for it. Expression. We have this x squared plus y squared equals to 25. How do you want to get like x a function? And we want to is y x. So this is the first thing we need. And now we're gonna start derivative both side is dx squared plus x plus squared to a 0 because 25 is constant. A 0 is derivative of constant. We have this is 2x plus 2y dy dx equal to a 0. Move to the expression to the other side, we have 2y dy dx. It is going to be negative 2x. And dy dx is going to be a negative x over y. Because 2y, 2x, it is the same as x over y. So just make this cancellation factor, and this is also the equation that you define. This is also the equation. And apply. Let's do another example. Example number 2. Find the equation of the tangent line to the curve. Say it is x squared plus y squared equals to 100. And at point six and 8. Okay, now let's just move. It's kind of the same process to find like x. So we differentiate both sides. X squared plus dx over y squared equal to dx 100. And that is 2x plus 2y dy dx equal to 0. And we move to the side to some algebra, and it is 2y dy dx. It is negative 2x. Then dy dx is negative x over y. At point 6, 8, the slope of a tangent line, it is negative 6 over 8, it is negative 3 over 4. And point slope form, we have is y minus 8 to negative 4, x minus 6. And what we have, it is going to be negative 3 over 4, we're going to form 18 of the root 2 plus 25 over 5, 25 over 2. It's the equation of the tangent line. It's 6, 8. Another example is, try it. Let's try it. Example number 3. Find the slope and define find the slope of the tangent line. To the function to the curve y minus y squared x squared plus 2 plus 2 1. I'm perhaps just to make out a point here, right? X equal to 2. What is the arm? What the hell? Okay, it's the same process, just implicitly differentiate this time. So we treat as a product rule. But yeah, treat them as a product rule this time. And this k dx of x squared y minus dx of y squared x squared equal to 0. And we just if we differentiate x, the y as being fixed, do not remove y. We keep them as y. Use the product rule. That is x squared dy dx minus is we keep y squared. This time is like 2y squared dy dx minus and plus is 2xy squared is 0. When differentiating x, there's no need to write out dy dx, just when you determine y, write out dy dx. This case is it combined the 1, 2 term and their dy dx. X squared dy dx minus 2y x squared dx is equal to those 2 terms there will be like a negative 2xy minus 2xy squared. We'll combine it and we try to get what is dy dx. Now we just combine them into x squared minus y x squared dy dx is equal to negative 2xy and negative 2xy squared. Move this to this side, just multiply 1 over this expression. You get is dy dx. It is a negative 2xy and a negative 2xy squared over x squared minus 2yx squared. This is expression. And to find the slope of the tangent line, you just plug in x equal to 2.
this, you can say it's y dx 2 is going to equal to 2. It's going to be like a negative 4y minus negative 4y minus negative 4y squared. This expression is going to be 4 minus 8y.
This is like the slope of the tangent line. Just leave it there. Okay. And let's do another example. Let's go to example 4. Implicitly differentiate the expression. Say effects can apply plus like 6 secant of x equal to 4x. Just use the product rule and implicit differentiation. 7 equal to dx x cubic and the y plus dx y to the 6 secant of x. And use the product rule. This time will be this 2x away. There's a 3x squared and y plus x cubic secant squared y dy dx plus 6y5 secant of x y prime. Note that y prime is the same as dy dx, and then just because I'm kind of running out of space right here. 4, and then just this time we can write y prime because it's easier. So 3x squared into the y plus x cubic secant squared of y and the y prime plus 6y5 secant of secant of x y prime And then we just take this, the x we have is 6 is secant of x and tangent of x. Remove the term of y term together. And we have this expression. It's going to be x cubed secant squared of y. And plus this. Secant of x. Whether by prime is 4 minus x squared and y. And this term doesn't have a like 6. We can have x and can have x. Okay, then we move to like another side, just that's like prime is 4 minus 3x squared 5 minus 6 to the secant of x and tangent of x. And this is the bottom. August storage. I don't know what is happening. Six by 5. Secant of x. That's his expression of d1 dx. It's quite prime. Let's try another example here. This one is more like a harder one. We introduce the chain rule. This is related. Example 5. Implicitly differentiate expression have to be e for x plus 2y, a exponent is equal to x squared minus natural log xy. Wow, this seems like complicated, right? actually is not that bad. If we do some chain rules, and we just do dx of the 4x plus 2y equal to dx of x squared minus dash y minus y. Just to have like a 4 x plus 2y. We're plugging in 2 this time. This one fixed x, but just to put a y in there. So we can have this 2y prime x plus 2y equal to 2x. But this time be careful. It's like if we differentiate the y, differentiate the x. And this time we just I forgot. So this time it's gonna y to the cubic over x y to the cubic. Y minus again is 3x y prime get over x y to the cubic. I forgot it's like cubic a little better. So it's my fault. I apologize for that. Then we combine with the term with dy. Only the y prime here. And it's 2 x plus 2y prime plus is 3 xy cubic with 3x squared. And over this 3xy squared over something cubic and y squared. And then we have the 2x minus 4x plus 2y minus y cubic over x cubic. We're going to do some algebra here just to simplify the equation. What we have is 2x plus 2y. Simplify this out as the 3 over y. And then y prime is going to be 2x minus 4x plus 2y minus 1 over x. Right underneath that y exponent. So there's 2x minus 4x plus 2y minus x to the 1 power over is 2 over 3 4x plus 2y plus 3y up to 1. This is the expression kind of like I feel more like now I'm doing not an example, but it's more like application of the. But no, I think that's probably just all for frequency differentiation. So I'm going to do like a brief summary of what it did. So one, when differentiating x variable just fix y when differentiating y variables right now dy dx. Y prime or dy dx. And some rules to use is derivative rules. Create just a product rule. Constant rule. And chain rule. Actually, by the end, I want to say another derivative rules. It is so the next one over x is 1 over x. Okay, that's all for 3.5. Implicit differentiation. In next video, in next video, we can talk about section 3.6, which is 1% differentiation. Thank you so much, and have a good day.